In this next part, we're going to look at increasing and decreasing functions. So we have two definitions here. The first is that of an increasing function. Given that a of n is the nth term of a sequence, then if an plus 1, which is the one after it, is greater than an for all values, then, by the way, that's strictly greater than. Okay, just remark on that. For all n, then the sequence is said to be increasing. And this implies that the ratio of the two numbers, a of n plus 1 divided by a of n, is greater than 1 for all n. Okay? We can say the same thing about the decreasing functions is the opposite case. Given that a of n is the nth term of a sequence, then if a of n plus 1 is less than a of n for all n, again all values, and less than, then the sequence is said to be decreasing. And this implies that the ratio of the two numbers, a of n plus 1 divided by a of n, is less than 1 for all n. Look at some examples here. This is one we've seen earlier. A of n is simply n. For n equals 1 to infinity, that is 1, 2, 3, 4, and so on. That is an increasing function. The next one is each successive number is larger than the previous number. A of n, where that is equal to n 1 minus n, so that would be start from 0, minus 1, minus 2, and so on. That's an example of a decreasing function. Okay, third example here. A of n equals 1 plus this term here, minus 1 to the power of n over n. This is an example of a sequence that is neither increasing nor decreasing. It neither increases nor decreases. Look at this here. The first term is a1 equals 0. A of 2 is 3 over 2. So that's minus 1 squared over 2. And then, yeah, that plus 1. And that's equal to 1 plus 1 over 2. 1 squared equals, minus 1 squared equals 1. And then we have the next term is a3 equals 2/3 and so on. So we have an increase here. Then we have a decrease. Then we have an increase again. So that sequence there is neither increasing or decreasing. So they don't all increase, they don't all decrease. The next thing we're going to look at is the idea of a convergent sequence and a diverging sequence. So let's look at this example here. A of n equals 1 minus 1 over n. And there's the first few terms there. 0, 1/2, 2/3, 3/4, and so on. It's obvious that the terms in this sequence are going tend to approach 1 as n gets larger and larger. So if you consider the 1000th value, a of 1000, that's equal to 1 minus 1 over 1000. And that's roughly equal to 0.999. So it gets quite it approaches 1 as n becomes larger and larger. So we can state this here, that it approaches 1 as n goes to infinity. So that's actually a verbalization of this line here. That's how we might verbalize it. And that line there. Put that in green actually, just to, there we go. As n becomes larger and larger. So we can say that 1 is the limit of the above sequence as n goes to infinity. Just as a quick remark there, limits are a very important part of mathematics. Now, if a sequence has a limit, then we say the sequence is convergent, and that the sequence converges to that limit. But on the other hand, we could have a divergent sequence. So let's look at this example here. Comment. In order for a given sequence to converge to a limit, L is some number. What we really mean is that the difference between each successive number and this limit gets smaller and smaller and smaller as n gets larger and larger. Just a sort of another example, that previous example I used, a of 1,000. If I was to go to the difference between a, that was converging to 1. So the absolute value of 0.999 minus 1 is equal to 0.001. Again, look at the absolute value sign. So as I get larger and larger values of n, this value here, this difference here, this absolute difference gets smaller and smaller. If I was to do it for n of a of 1 million, I'll be looking at 1 millionth here. So it gets smaller and smaller as n gets larger and larger. Not all sequences have a limit. Take, for example, any unbounded sequence. Okay. Now, another remark: if a sequence has a limit, it is the only limit there is for that sequence. Okay. Now, elementary properties of sequences. So, if the values of one sequence converge to A, and the values of another sequence converge to B, if these are convergent sequences, then if we were to add the terms in A and B, in sequences A and B, then the sum of those numbers, the summation sequence C, that will converge to the limits, so to speak, of both A and B, the sum of A and B. Likewise, if they are, this is the same rule applies for the product. So if we were to multiply A of n by B of n to get C of n, that sequence of case-wise products will converge to A times B, the product of the limits for for the sequence A and the sequence B. And again, if we can do that for the quotients A divided by B, as long as B is not equal to 0, we can say the same thing for the quotients. So essentially, if you're coming to these couple of elementary properties of sequences apply when you are dealing with combinations of sequences. Now, the mathematics there looks actually quite tricky, or sometimes the notation can get a bit overpowering, but when you look at a few examples, you'll sort of see that it's actually straightforward.